All right, last video lecture for the solutions unit has us covering the process of combining solutions and finding the new concentration after that. So let's say that I add two solutions of different concentrations together. So I have in the beaker 0.5 molar NaCl, and I'm going to add 4 molar NaCl to it. How can I determine the concentration of the resulting solution? That is what we're going to cover today. So when you combine two solutions, let's go back and review the molarity calculation that says that molarity is equal to moles of solute divided by liters of solution. When we combine two solutions together of differing molarities, all we need to do to find the molarity of the combined solution is take the total moles of solute divided by the total liters of solution, which means that we need to find moles of solute in our first solution and add it to the moles of solute in our second solution. If there's a third solution, we'd also add that in, but I'm typically going to keep it to 2. And then we would divide by the total liters of solution, which means that we would add the volume of our first solution and the volume of our second solution. And if there's a third solution, we'd add the volume of that. But again, I keep it typically to 2. Once we divide that, that is going to be the molarity of our combined solution. So we're basically doing the molarity equation just with a couple extra steps. So for example, let's say that solution 1 contains 50 milliliters of 1.4 molar HCl. Solution 2 contains 120 milliliters of 0.5 molar HCl. We want to know the concentration of the new solution once these are added together. So let's start with solution 1. So we need two things. We need moles of solute from solution 1 and the volume. We have the volume, it's 50, but we need to figure out moles of solute in solution 1. So I'm going to utilize the equation N equals V times M. I'm going to convert my volume into liters because I'm using the molarity equation. So 50 milliliters, move the decimal 3 spaces to the left to get 0.0500 liters, because again, I need to maintain proper sig figs. So I need 3 still. I can plug that into the equation with the 1.4 molar number that I have, and I would get that my moles is 0.07 from solution 1. For solution 2, I need to do the exact same thing. I need both the moles of solute in solution 2 and the volume. I have the volume, I need to find moles. So I can first off convert my volume into liters because I'm using the molarity equation and volume has to be in liters when I use that. So 120 milliliters, move the decimal 3 spaces to the left, maintaining 3 sig figs would get me 0.120 liters. Plug that along with the molarity into the equation, and I would have a mole value of 0.06 moles of HCl in my second solution. So bringing over some of that info real quick, we found moles of solute in solution 1. This was the volume in liters. For solution 2, this was the moles we just calculated out and the volume in liters. So my molarity of my new solution is equal to total moles divided by total liters of solution. So I'm going to find my total moles by doing 0.070. So that's moles from solution 1 plus 0.060 moles from solution 2 to get a total of 0.13 moles to proper sig figs. right? Addition, we add and look after the decimal. So we have 2 after the decimal here, sig fig wise. 2 after the decimal here, sig fig wise. So our answer should have 2 after the decimal here, sig fig wise. Our total liters of solution, we're going to take the 0.0500 from solution 1, add it to the 0.120 liters of solution from solution 2. We're again adding, so we look at sig figs after the decimal. We have 3 here and 3 here, so we should have 3 after the decimal in our answer, which is why it's 0.170 liters. Then we can take our total moles, which is 0.13, and divide it by our total volume in liters, which is 0.170. Rounding to proper sig figs, now we're dividing, so we look at total sig figs, right? This one has 2 sig figs, this one has 3, so we'd round our answer to 2 sig figs, which it would come out to 0.76 molar. And that would be the concentration if I actually combined these 2 solutions. Now there's an easy way to check this, right? Our answer should be between our 2 initial concentrations, because I'm adding them together and it's sort of averaging out. So 0.76 does fit between the 2. It's not always going to be directly in the middle, unless I'm adding an equal amount of both solutions together. But it's a nice way to check just to make sure that it's in the middle. It should be closer to the solution that you have a higher volume of. So it makes sense that it'd be closer to the second solution's concentration because I added more than double the amount of solution 2 compared to solution 1. For example 2, we have 100 milliliters of a 1.5 molar solution added to 200 milliliters of a 2.5 molar solution, and we want to know the molarity of our new one. So again, for solution 1 and 2, we need 2 numbers, the number of moles of solute and the volume of solution. We have the volume, we need to find moles, so we're going to go through the same process we just went through. Converting our volume into liters first, maintaining sig figs, so 100 milliliters. Move the decimal 3 spaces to the left to get 0.1, and maintaining 3 sig figs would be 0.100 liters. Plugging that in the concentration into the equation, we can solve for N, which would be 0.15 moles to proper sig figs. We have 3 sig figs here, 2 here, so our answer should have 2. For solution 2, we need the same things, number of moles of solute and volume of solution. We have the volume of solution, but we need to find moles. So I need to start by converting the volume from milliliters to liters. 200 milliliters, move the decimal 3 spaces to the left, becomes 0.2 liters. Maintaining the 3 sig figs, it becomes 0.200. We can plug that into the equation along with the molarity, and we would find that we have 0.50 moles in solution 2 to proper sig figs because we have 3 here and 2 here. So we should have 2 here. Now that I have moles of solute for both solutions and a volume for both, bring those over to the next slide. So this is just the moles we calculated, liters of solution for both. We know that the molarity of our new solution is equal to the total moles divided by total liters of solution. So we can add the moles together, 0.15 from solution 1 plus 0.50 from solution 2. Well, since we're adding, we look at sig figs after the decimal for rounding. So this has 2 sig figs after the decimal, 2 sig figs after the decimal. So our answer should have 2 sig figs after the decimal. For liters of solution, we're going to add 0.1 to 0.2, maintaining or using sig fig rules, I should say. So we have 3 sig figs after the decimal here, 3 after the decimal here, so we should have 3 after the decimal here, which is why it's 0.300 liters. We can then divide total moles, which we just found up here, by the total liters of solution, which we just found right here, and we would get an answer out of 2.2 molar for our new solution. Sig fig wise, since we're dividing, we have 2 sig figs here, total, 3 sig figs here, total, so we should have 2 total sig figs in our answer, which is why it's 2.2. For the third example, we have 75 milliliters of an ammonium chloride solution containing 160.5 grams of solute is added to 0.125 liters of a 2.5 molar ammonium chloride solution. We want to know the molarity of the new solution. So remember, we need 2 numbers for each solution. We need the number of moles of solute, and we need a volume in liters. So let's start with solution 1, which is an orange. Let's start by converting our volume of 75 milliliters into liters. So we would move the decimal 3 spaces to the left, turning 75 milliliters into 0.075 liters, maintaining the 2 sig figs. For moles, it's not the same as we've been doing because we were told the amount of grams of solute. We were not given a molarity. So that means that we can just do compound stoich to convert 160.5 grams of ammonium chloride into moles and use that. So for that, we would plug the 160.5 grams of ammonium chloride, which is NH4Cl, in the upper left-hand box. Bring grams of NH4Cl diagonal down. Figure out how many grams are in 1 mole. So that's just a molar mass calculation. Comes out to be 53.5. When we do 160.5 divided by 53.5, we get exactly 3 moles. However, sig fig wise, we need to round to the same number of sig figs as our starting number. So that's why it's 3.000, because 160.5 has 4 sig figs, and we need this to have 4. So now I have my moles of solute. I have my liters of solution for solution 1. Now we can focus on solution 2. Solution 2, to find moles of solute, we can just do the molarity times the volume. And our volume's already in liters, so we can just plug 0.125 liters in for V, 2.5 M in for M, solve for N, which is 0.31 moles. So now that I have moles of solute for solution 1 and solution 2, and liters of solution for both, I can do total moles divided by total liters of solution to get my molarity. So to find my total moles, I'm going to do the 3 moles from solution 1 plus the 0.31 moles from solution 2. Rounding to proper sig figs would be 3.31 moles. Sig fig wise, we're adding. So we look at sig figs after the decimal. We have 3 after the decimal here, 2 after the decimal here, which means we should have 2 after the decimal in our answer. Keeping in mind, the 3 is still significant. We just don't use it to round. For our total liters, we would do the 0.075 from solution 1 plus the 0.125 from solution 2. Rounding to proper sig figs, it comes out to 0.20 liters. We're adding, so we look after the decimal for sig figs. We have 2 after the decimal here, 3 after the decimal here, so we should have 2 after the decimal in our answer, which is why it's 0.20. When we divide the 2, the 3.31 divided by the 0.20, it comes out to be like 16.55, I believe, but we need to round it to 2 sig figs total, which is why we round it to 17 molar. We do not have information in the problem for us to check if that works, if that's between the molarities of solution 1 and solution 2. However, we could actually calculate the molarity of solution 1 by doing the moles of solute divided by liters of solution. If you do that, it does come out to be 40 molar. So it would make sense that our answer should be somewhere between 2.5 and 40, which 17 is. And that is it for the solutions unit.